Hello friends, so continuing with our constitutive analysis discussion, the present lecture we will be covering the relatively higher strain rates, okay, where we do actually hot working, okay, and actually we have missed the part where we can cover superplasticity, but I am not doing that right now. So we have covered very low strain rate where creep is important. Okay, and then next one in high temperature deformation, the strain rate which comes between 10 to the power minus 5 to let us say 10 to the power minus 1 or minus 2. Okay, there you can see superplasticity in material, and then we can come to the hot working processes like the conventional one like rolling, forging and extrusion, okay, from 10 to the power minus 1 to at least 10 to the power 2, okay, and even higher strain rate more than 10 to the power 2. Okay. So, we will see two models here right now, which is still going to come under phenomenological model, okay, which covers relatively higher strain rate more than 10 to the power 2 and the strain rate where you do the hot working. Okay. So, that analysis will be more. Okay. So, slightly the sequence is little bit different. We have done very slow strain rate, now we are doing relatively very high strain rate 10 to the power 2 and more, and then we will be discussing about the hot working, which is the main focus of our discussion. So, again phenomenological based constitutive equations, okay, and so the constitutive equation for high strain rate deformation, okay. So, as I was telling you that in this case my strain rate will be more than 10 to the power 2 strain rate, okay. One of the most important or used model is what we call as Johnson-Cook model, okay. This model takes care of all the three parameters basically, because here again you can see that we are working on very high strain rates, okay. So, there is not enough time for dislocation to recover, okay. So, strain hardening is an important consequence of that strain hardening will be there in this type of deformation, very high strain rate deformation, okay. And this Johnson-Cook model is the one of the most used model in that segment, okay. And I am only discussing couple of model in each of this category, okay. Actually, if you go to any review paper or something like that book, okay, then you will see there are large number of models with slight variation, okay, or sometimes the more famous models are modified for particular material or particular condition. So, this is not a exhaustive list, okay. You have very large number of models in each of these categories, okay. I am just covering maybe one or two just to give you a flavor of the whole idea of constitutive equation development, okay. So, if you see here the stress is dependent on the all the three parameters. So, you have a strain and a strain hardening exponent, then you have a strain rate, okay, and then you have a effect of temperature. The strain rate is in the form of strain rate some star, which is basically you are normalizing it with some reference strain rate, okay. Similarly, temperature is being normalized here, okay, and it is used as T star, okay. So, the other parameters are A and B are A is the yield stress at reference temperature and reference strain rate, okay, and B is the coefficient of strain hardening. So, of course, because it is coming here, so it has to be coefficient of strain hardening. N is strain rate hardening exponent, okay, sorry, strain hardening exponent. Cm are the material constant which represent the coefficient of strain rate, okay, strain rate hardening and thermal softening respectively, okay. So, one of the important idea which you should understand here is that when we do any high strain rate deformation, okay, whether in hot working or in this case even higher strain rate is more than 10 to the power 2, okay, there is always a temperature rise in the material. Actually, you understand that when we are working on the material, when we are deforming the material, we are inputting energy into the material. Okay. So, some energy which you are inputting goes in the deformation process, okay, that means plastic deformation, and some energy goes in form of heat. Okay. So, there will be heat generation whenever you do deformation, that you can also experience when you are, for example, you take a metallic wire and you do repeated deformation like this, and you will, if you touch the material after some time, it will be sufficiently hot, means you can easily feel it. Okay. So, the heating will always takes place when you are working on the material. Some energy will go in, of course, in the deformation process, but most of the energy goes in heating the material. When you are doing at a slower strain rate, okay, this heat has you are giving enough time for this heat to dissipate. Okay. So, there will not be any temperature rise in the material as such. But if you are doing a deformation at very high strain rate, then you are not giving enough time for this heat to dissipate, and that is what we call as from your thermodynamics you must be knowing, that is what we call as adiabatic heating. That means when you are not allowing, or adiabatic temperature rise, because you are not allowing heat to dissipate. So, you have created a adiabatic condition. So, at very high strain rate, when you are deforming, the temperature also, because you are not allowing heat to dissipate, temperature will rise above the temperature of deformation. So, for example, you have set the temperature of deformation as 900 degree Celsius, and you are doing a very high strain rate deformation. What will happen? The temperature will rise to 950 degree Celsius. I am just taking an example. Now, this 50 degree rise, you should understand that temperature will always come in the exponential term. Okay. So, stress is dependent exponentially with at temperature. So, linear rise in temperature will give a exponential rise in the, or in this case exponential drop in the stress. Okay. So, what you are measuring the stress is, you are thinking, and because when you develop the constitutive equation, you will take temperature as 900 degree Celsius, because you are thinking that you have done at that, your furnace was set for that, but actually the material is deforming at 950 degree Celsius because of adiabatic heating. So, you have to compensate for this temperature. So, this temperature, so basically what you have to do is, you have to change the stress level, okay, to compensate for this temperature rise. Okay. And that is as I was telling you, that there is exponential dependence between temperature and stress. So, basically if you plot log sigma versus 1 by T, okay, then you will be able to know that what is the dependence of stress on the temperature. So, any rise in the temperature will be, you will be able to compensate by changing the stress. Okay. So, basically you have to bring down the temperature from whatever you have measured is for 950. So, you have to bring down that stress for 900. That means if my in a stress strain curve, if this is my stress which I have measured, after the compensation the stress will be obviously higher than that, because the temperature will be low, should have been lower than that. Okay. So, this type of temperature compensation in stress you have to give when you are doing at very high strain, when you are doing a high strain rate deformation. Okay. So, just I forgot to bring it out earlier. So, I am doing that now. So, basically Johnson-Cook model, if you see, okay, it contains 3 terms. So, the first term brings out the effect of strain on flow stress. Okay, you have a strain term with a strain hardening coefficient. The second term brings out the effect of strain rate, okay, and the third term bring out the effect of temperature on the flow stress. Okay. So, all the 3 parameters, the important parameters are considered in the flow stress term. However, in this Johnson-Cook model, the parameters are considered to have an independent effect. That means, independently change in strain rate is not going to affect the or not going to influence the temperature and strain. Similarly, independently changing temperature is not going to affect the strain and strain rate and so on, and there will not be any effect of so on the stress there will be only the effect of change of stress temperature, okay, and there is not going to be any effect of strain and strain rate, okay, which is usually may not be the case, because there are always interdependence and there is a interdependence of all these parameter, and they sometime kind of have a combined effect on the stress. Okay. So, but Johnson-Cook model was a very simple model, and that is why it is very popular also, because you can easily use this model to make a constitutive equation. So, for a rough kind of work you can easily use it very quickly. However, some modifications were proposed by other researchers on this model to take care of this coupling effect. Okay. One of the model I am just discussing it here, which was proposed by these two gentlemen, okay, Ural and Caro. Okay. This is the reference for that. They have modified this Johnson-Cook model. Okay. They have suggested some modification. So, they have coupled temperature with strain hardening. Okay. So, that they have proposed that it should be the temperature and the strain hardening should be coupled, because when you increase the temperature there is always going to be effect on the strain hardening exponent. Okay. So, these are not independent. Enhancement in strain rate sensitivity in the dynamic regime with a smooth and continuous transition between two distinct deformation regime. Okay. So, strain rate sensitivity is also going to be affected by in the dynamic regime, okay, and there will be a temperature dependent strain rate sensitivity also. So, you should understand that these are all parameters are all coupled to each other, okay. So, we cannot treat them independently, and there are lot of modifications were proposed by different researchers on Johnson-Cook model. But for a quick development, this is a very good model if you are working in a high strain rate regime, that is more than 10 to the power 2, to use a Johnson-Cook model for any to understand or to model any deformation process which is working at that particular strain rate. Okay. So, this is for high strain rate deformation. Now, we are going to discuss the constitutive equation for hot working. Okay. So, now again my strain rate range is, let us say, from 10 to the power minus 1 to 10 to the power 2 strain rate. Okay. So, in this regime we are looking at the constitutive equation, and again you can relate it with what we were discussing during phenomenological constitutive equation, that these phenomenological constitutive equations are developed for different temperature and strain rate regime. So, you can also now see very clearly that for different strain rate windows we are developing different type of constitutive equations. One window we have developed for creep kind of deformation, okay. One we have already developed now for very high strain rate, more than 10 to the power 2, okay, and the look of the equations is quite different. Okay. So, for each regime you have to develop different set of equations, and in that regime also there are multiple models. So, you should not consider that there is only one model, there are multiple models to relate the stress with these three parameters. Okay. So, in this particular regime we are going to discuss this Arrhenius type equation, okay, which relates the stress as a function of temperature with exponential term. Okay. So, basically again we are developing relationship between stress, strain rate and temperature, and this particular equation was proposed by these two scientists, Sellers and Taggart. Basically what it is doing, okay, so you have Z again Zener-Holloman parameter, okay, which bring out these two parameter together, strain rate and temperature, okay. Of course, our temperature will always come under exponential term, okay, and they relate this Z with the stress, okay. We are taking here P, I am using it for saying peak stress, okay. So, when you are deforming the material, okay, if you remember, if you have a single peak, this is my peak stress sigma p, okay. So, you can use sometime you can use steady state stress, okay, or peak stress, okay. So, here we are using peak stress to find out the constitutive equation, okay. So, this is this stress is actually related with Zener-Holloman parameter here by this sign hyperbolic equation, okay. So, this is a very general equation, a sign hyperbolic equation to relate the stress with the Zener-Holloman parameter, okay. And of course, there are a couple of constants here, alpha, a and stress exponent n, okay. So, different constants are there. So, a, alpha, n are experimentally determined constant, and also q is also going to be determined experimentally only, and it is activation energy, okay. Alpha is because you can see it is multiplied with the stress, it is called stress multiplier, okay. And what it does is it brings alpha sigma in correct range, so that we get linear and parallel relationship between ln epsilon dot and ln hyperbolic alpha sigma p, okay. So, basically this is we use this multiplication, okay, with alpha we use to bring the whatever plots we are going to get, okay, they should be all linear first, and they should be all parallel to each other. That means they should have similar deformation behavior, okay. So, for that it is kind of a adjustment parameter you can say, which is we are multiplying with sigma t, okay, to bring these two curves linear and parallel. We will see these curves, so then you will be able to understand that what we mean by that, okay. Now, this Arrhenius type of equation, this general equation. So, I would call this hyperbolic equation as a general equation for a very large strain rate range, okay. That is my general equation for a very large window of strain rate. Of course, when you are talking about strain rate, it is ultimately stress is also going to be related to that. So, at low stress, this same equation can be reduced to a power law equation, okay. Already we have seen this type of equation, okay, a power law equation where epsilon dot and sigma p is related with a some exponent n prime here, okay, and again temperature is in exponential term, okay. So, this is one type of relationship where the epsilon dot and sigma p are related with some exponent here, and whenever you have this kind of equation, okay, let us say I would say a equal to b and raised to power something, okay, let us say q here, then these are called power law equation, okay. There is a power over b, so that is why it is called power law equation. So, so at low stresses you will have this power law equation, okay, and incidentally this type of equation is also valid for superplasticity, okay. So, there also you have a power law equation. As you go to higher strain rate, okay, and basically higher stresses. So, there is a mistake here, I would write is a higher stresses. So, where alpha sigma is more than 1.2, then this generalized equation can be reduced to a exponential equation, okay, which is given by equation like this, okay. There is no exponent here now, but there is a multiplication of a new constant which is called beta. Okay. So, beta sigma p is there, but the sigma p instead of power now has come in the exponential term, whereas here it was not in exponential term, but there was a power over it. Okay. So, these are some subtle changes in the way we are writing constitutive equation for different strain rate regime. Okay. So, sine hyperbolic is a generalized equation, and these are equation for a specific domain. So, for low strain rate, low stress condition, you will have power law equation, but there is a power law breakdown as you increase the strain rate. Okay. So, at higher stresses you have this exponential dependence of strain rate on the on your stress. Okay. So, this the multiplication here beta is actually again there is the same alpha, the stress multiplier is there, and the n prime exponent which is in the power law equation. So, you have to multiply these two to get beta. Okay. So, these are the different variation of the constitutive equation in different strain rate regime. Okay. So, now we will use this all these particular equations, okay, to calculate our all the parameter of our constitutive equation. Okay. So, you can see in this particular constitutive equation you have q which you want to know, there is a n which you want to know, okay, there is alpha which you want to know. Okay. So, these parameters are required for development of the constitutive equation. Okay. So, calculation. So, first we will start with the calculation of n prime, okay, which is shown here. Okay. So, calculation of n prime, okay, equation is this, which is basically our power law equation for lower strain rate and lower stress condition. Okay. So, this is my power law equation. So, epsilon dot is related with sigma p to the power n prime exponential minus q by r t. Okay. Again we will do the same thing. Okay. If I take log on both sides, then ln epsilon dot ln of a1 plus n prime will come down now, ln of sigma p, and exponential will go minus q by r t. So, now if I plot a curve between ln epsilon dot, okay, and ln sigma p. Okay. So, that is what we have plotted here in this figure. Okay. You have plotted ln epsilon dot and ln sigma p. Okay. Then the slope of this. So, if I differentiate this equation, okay, so of course, the constant terms will go become 0 and then n prime will become. So, at constant temperature, so this will also become 0 at constant temperature, and this is obviously a constant. So, these two terms will become 0, okay, and so n prime will be equal to del ln epsilon dot upon del ln sigma p. Okay. So, basically it is the slope of this curve. Okay. So, these three equations or these three curves are at for these three different temperatures. Okay. So, basically how we have got this these data. So, at 115 degrees Celsius you have deformed the material at different strain rates, 3-4 strain rates for example. Okay. From there you have got this 4 or 5 data points. Then again 850 degrees Celsius we have deformed for 5 strain rate. So, 1, 2, 3, 4, 5, again 5 data points and so on. So, for each strain rate what was the stress that is measured, you take logarithmic of strain rate and logarithmic of ln of sigma p, and that will give you these 3 straight lines, more or less these are parallel. Okay. That means there is no change in the deformation behavior at these 3 temperature. So, I can take the slope of these particular curves as n prime. So, this is how I am going to get the n prime for my constitutive equation. Okay. Now, the next parameter I want to know is beta. Okay. So, beta is what we saw in the other one, the exponential equation, which was valid for higher strain rate or higher stress condition, alpha sigma more than 1.2. Okay. So, you have this beta term here. okay, and beta, as I told you earlier also, beta is equal to alpha n prime. So, n prime already we have calculated, okay. Now, we want to know beta here. So, again from this equation beta will be I can again take ln of this equation. So, it will be ln of epsilon dot equal to ln of A2 plus this exponential term. So, it will be simply b sigma p, and this is also exponential term. So, it will be minus q by RT. Okay. So, again taking at constant temperatures. Okay. So, we will take the constant temperature here. So, again this term will be 0, this will be 0. Okay. So, beta will be simply, if I differentiate beta, okay, or if I take if I differentiate this, then this will become 0 and this will become 0. Okay. So, this will be 0, this will be 0, okay, and this beta will be del ln epsilon dot upon del p, del sigma p. In n prime it was del ln of sigma p. So, now it is del sigma p. So, what we have plotted now, sigma p on the x axis, ln epsilon dot on y axis. Okay. Again you can see you have got some straight lines, okay, straight line fit is there, again at three different temperature for different strain rates, okay, and from the slope of this you will be able to get beta. Okay. Now, we will calculate, will do the calculation of n. Okay. So, already you can see that I have got the alpha parameter here, because I know beta, I know n prime. Okay. So, alpha will be simply equal to beta upon n prime. So, alpha means alpha is automatically calculated once I know the beta and n prime, these two parameters. So, now I want to know what is the calculation for n. Okay. So, already we have seen this equation, the sine hyperbolic equation. So, z, which is this, okay. So, this is equal to actually z epsilon dot exponential q by RT equal to a sine hyperbolic alpha sigma p to the power n. Okay. So, here it is n, in the power law equation it was n prime. So, that is the difference. Again we will take the ln on both the side. So, ln epsilon dot, okay, equal to ln of a plus n will come down, ln of sine hyperbolic alpha sigma p, and if you would have taken ln here it would have been plus q by RT, but you have taken it on the other side of the this equal to sine. So, it has become minus q by RT now. Okay. So, ln epsilon dot equal to ln of a plus n ln sine hyperbolic alpha sigma p minus q by RT. Okay. So, now again you can differentiate this equation. So, again I can differentiate this equation. If I do a differentiation, okay, this will again become 0, and if I am doing for constant temperature, this will also be 0 and this will also be 0. So, n will be equal to ln epsilon dot del ln epsilon dot divided by del ln sine hyperbolic alpha sigma p. Okay. So, now what I am going to plot is ln sine hyperbolic alpha sigma p on the x axis and ln epsilon dot on the y axis. Okay. And now you can see that we are again doing it at constant temperature for different strain rates, okay, and these are now linear curves obviously and also parallel. That is what was the purpose of using alpha, okay, to make these graphs as parallel and linear. Okay. So, from the slope of these curves now, okay, you will be able to find out what is the stress exponent n. Okay. So, this is how actually you will do calculations, okay. That is why I am doing the whole calculation in front of you, so that once you have data you can do all this calculation yourself. All these things can be easily done on any spreadsheet, whether you want to use Excel, Origin, okay, or any other software, okay, it does not matter. you can use it very nicely. You just have to take logarithmic and taking sine hyperbolic, multiplying by something and so on. Okay. So, and once you have the plot, you can find out the slope very easily by fitting a trend line and finding the equation of that straight line. Okay. So, slope will give you the value of n. Okay. So, all these things you can do very easily using any software. Okay. Now, we want to know that what is the activation energy. Okay. So, calculation of activation energy. For calculation of activation energy, our temperature will change. Okay. And strain rate will remain same. Okay. And also please note down, I forgot to mention it earlier, that these are all apparent activation energy. One activation energy you also get from the diffusion data. Okay. Those are true activation energy. These are apparent activation energy. The reason is because the microstructure is continuously changing during the deformation. Okay. And these are not activation energy calculated from one specific mechanism. Okay. We are trying to predict a mechanism using the activation energy. Okay. So, the microstructure is not going to be a stable microstructure, or for example, you are deforming at different temperatures here. Okay. So, now maybe if you are deforming at different temperatures, earlier also if you remember we were seeing in dynamic recrystallization, okay, that as you change the temperature, the flow curve changes from a single peak where it shows discontinuous dynamic recrystallization to multiple oscillating peak kind of stress strain curve. Okay. Also if you remember, we were seeing some flow stress curve where at low temperature it is showing strain hardening, then at some intermediate temperature it shows dynamic recovery, then even at higher temperature it shows dynamic recrystallization. So, steady state, sometimes softening and so on. So, the idea is that the microstructure is continuously changing, it is dynamic. Okay. So, when we are calculating the activation energy from the data of different temperatures, okay, the activation energy which you are getting is going to be a apparent activation energy. Okay. If you want to calculate more accurate activation energy, what you should do is, when you are deforming at a strain rate, let us say you are deforming at 0.1 strain rate. Okay. So, what you do during the deformation itself, you change the temperature. Okay. And because then the microstructure has not changed, it would not have been different so much during a very short duration. So, basically you are deforming, let us say at one temperature, you change the temperature, deform it, bring it to again the same temperature, maybe go below and so on. Okay. So, by doing that, you are actually trying to have the same microstructure, and in the same microstructure you are changing the temperature, and for suppose this is T1, this is T2, this is T3, you will get corresponding stresses. Okay. So, then you will be able to say with more confidence that this is my activation energy of deformation. Okay. The way we are calculating is we are not doing it like this. Actually, what we are doing is we are doing test at different temperature. Okay. So, this is T1, T2, T3. Okay. So, T1 is more, then T2 is then T3. Okay. And suppose we have done this all at a constant strain rate. Okay. So, this is what we are doing now. So, again taking the previous equation where we took the logarithmic. Okay. So, this particular equation, okay, again we are using it here. So, ln epsilon dot equal to ln A plus n ln sine hyperbolic alpha sigma p minus q by r t. Okay. And again you are doing some rearrangement here. So, this we have kept here, and I am taking this on this side and ln A on this side. Okay. So, it will become q by n r and we are also dividing by n after taking it there. Okay. So, this will become positive when I take it here. Okay. And ln epsilon dot is already positive. Okay. And this ln A will become negative. Okay. And also I am dividing by n. Okay. So, now you do not see any n here. Okay. But you have divided by n. So, q by n r t plus 1 by n ln epsilon dot minus 1 by n ln A. So, slight rearrangement of the earlier equation. Okay. And dividing by n on both sides. Okay. So, you will get this equation. Okay. Nothing difficult here, and again we will do a differentiation. Okay. Now, this is at a constant strain rate. So, this is going to be 0. Okay, at a constant strain rate, this is already a constant. So, del ln sin hyperbolic alpha sigma p upon del 1 by t. So, 1 by t is my another variable, will be equal to q upon n r. Okay. So, for this what we will do? We will do a plot between 1 by t, which is shown here as t inverse t to the power minus 1, and ln sin hyperbolic alpha sigma p. Okay. So, if I do that, I will get again these curves. Okay. More or less all the curves are linear and parallel to each other. So, I would say that there is not much change in the deformation mechanism at different temperatures. Okay. So, now from the slope, okay, from the slope of this curve, this slope is equal to q n r equal to the slope, is not it, of this. So, to get the activation energy, I will multiply n r with the slope. Okay. So, this slope is equal to q by n r. So, if I multiply the slope with n into r, n already we have calculated earlier, r is your universal gas constant, then I would be able to get the activation energy for deformation. Okay. Usually activation energy for deformation which you get through this kind of processes comes very high, okay, compared to any known diffusion processes or solute diffusion processes. Okay. Because the dislocation movement also requires certain amount of activation energy. So, all those things get combined. Okay. And it is sometimes very difficult to assign any physical meaning to this kind of activation energy calculation. Okay. Sometimes it is difficult. So, with this we have completed the different calculations which we are going to do for development of the constitutive equation. Okay. So, the example we have taken for constitutive equation is the Arrhenius type of constitutive equation. Okay. So, whatever parameters are going to be required in that we have seen that how we are going to do the calculation. Okay. So, once you know that this is how you have to do calculation, you can do it for some other models also which you think is suitable for your material. Okay. And that will be able to give you a constitutive equation which you can use for doing, maybe if you are doing any modeling work, okay, FEM modeling or any other modeling for your deformation process. Okay. With that, thank you.